In this example, we're faced with a problem where we have a rigid bar supporting this crate of weight WC. The bar itself is supported by two rods there at ends A and B. And what we want to know is that as a result of the weight of the bar and the weight of the crate, what are the downward displacements of ends A and B of that bar? In other words, what is the elongation of each one of the rods 1 and 2. Our first task, of course, is to determine the axial load that's carried by those rods. So we will need a drawing here of the free body diagram of the bar. So if we look at first at these rods, they're carrying a load here of F1 and F2. By Newton's third law, equal and opposite force, which is acting on the bar at ends 1 and 2. This should be F1 over on the left-hand side. And then, of course, we have the weight of the bar, which is called WB, and then the weight of the crate, which is WC. So again, our task here is to determine the load that's carried by rods 1 and 2. So on the bar itself, I'm going to do first the moment equation about end A. The weight of the crate has a moment arm of B. It's going to be in the negative K. I need to explain that my coordinate axes here are going to be X to the right and Y up. The weight of the bar, that's in the middle, so it has a moment arm of L over 2. About A, it has a negative a moment. And then the load of F2 has a moment arm of L, and that's in the positive, the plus K. For equilibrium, that is a 0. So from this, we're able to extract that the load in rod 2 is B over L, that ratio times the weight of the crate, and half of the weight of the bar. That's just the way the equilibrium analysis works out. When we sum forces in Y, we have F1 plus F2 minus the weight of the crate minus the weight of the bar. For equilibrium, that is a 0. So from this, I get that the load that's carried by member 1 is going to be equal to WC plus WB plus F2, and F2, that's a minus F2. So it's going to be a minus B over L WC 1/2 WB. So F1 ends up being 1 minus B over L, the weight of the crate, and again, it's carrying half of the weight of the bar, which is what you would expect. So again, these are two key steps here. And maybe what I need to do is right from the word go, identify what I'm doing. I'm looking at equilibrium. The results we have there for F1 and F2 simply came from equilibrium. Now, for our elongation equations, we have a simple relationship to remember, and that is that the displacement downward of A is entirely due to the elongation of 1. So that's F1 times the length of 1 divided by E1, A1. F1 we have, that's the 1 minus B over L, WC, half of the weight of the bar, the length of rod 1 is H, and E is the same for both of them. We just call it E pi D1 over 2 squared. So D1 is the diameter of rod 1. The second equation is that the downward displacement of B is entirely due to the elongation of 2. So that's F2 L2 divided by E2A2. So F2, that's the B over L times the weight of the crate plus half of the weight of the rigid bar divided by the same value of Young's modulus E, pi d over 2 squared. And again, the length of 2 is h. So here it was just a matter of doing the equilibrium analysis to find the load that's carried by members 1 and 2. It's a very straightforward application of a moment equation and a force balance equation. Then using the elongation equations to get E1 and E2, that gives us the displacements downward of A and B.